for today. First thing I want to do is to screen share and just make sure that you're able to see what I see on my screen. Hold on one moment. All right. Can someone just give me a verbal yes that you can see what's on the screen?
Yes.
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 Great. Okay, then we are ready to start. And as always, if you have any questions, don't hesitate to interrupt me. I'll be glad to take your questions at any time. I'm going to start with several little charts that list clinically useful radionuclides. And as we go through them, I'm going to indicate the ones that I think you need to know specific information about. That information would be the physical half-life and the gamma ray energy. No one on any exam will ever ask you the percent abundance of any nuclide, but you do need to know what percent abundance means. Some people seem to think that percent abundance of nuclides has to do with the occurrence, the abundance in our universe. That is very, very far from being correct. In fact, the way we define it, as shown on the bottom of the slide, is that the percent abundance gives us an indication of how many photons are coming out per 100 disintegrations. And you might be thinking, look at the first one here, chromium-51 has a percent abundance of 9%. Now, you would think that if 100 chromium atoms decayed, it should give you 100 gammas, but it doesn't. And you might think, why not? And so we're going to go ahead to the next slide for a moment and take a look at the decay scheme, because that will have the answers to all of the questions related to percent abundance. So you see here that chromium-51 decays straight to the ground state of vanadium-51, 91% of the time. No gammas are given off, and you can tell that because associated with this line here, there are no vertical lines coming down that represent isomeric transition. But look what happens 9% of the time. Chromium decays to vanadium-51M. You all know by now that that is the metastable state. That's an excited state with a measurable half-life. And look what it does. It drops from the metastable state to the ground state. This vertical line down is a gamma. That mode of decay is isomeric transition. And here's the energy and the half-life. Here are the energy and the half-life. 320 keV. Do we like 320 keV for imaging? Not really. We want to be in the range of 100 to 250 keV. That's considered ideal. We can go outside of it. We do it all the time, but we don't like to, because when the energy goes below 100, think about thallium or xenon, or goes above 250, think about chromium, or more likely iodine-131, the image quality degrades. So this is why we're only getting 9 gammas. Only 9% goes through a metastable state, producing the gamma ray. Now, chromium is not one that I would recommend you know for an exam, because we almost never use it anymore for anything. F18, put a big star by that one. You must know 110 minutes and 511 keV. Now, what is the mode of decay of F18? Who knows? How does it decay?
Positron emission.
Right, so
Annihilation.
this decays by positron emission. And even if you didn't know that, just, so sorry, let me turn this. Even if you didn't know that, 511 keV tells you that annihilation has taken place. And when does that occur? That only occurs with positron emission. So here we have F18, 110-minute half-life. The energy will always be 511 keV. And take a look at the percent abundance, 180%. Now you might be thinking, from 100 decays, how could we get that many? But in fact, what is the maximum percent abundance that this could have been? We're getting 2 of these for every one of these that decays. The maximum percent could have been 200% because we're getting 2 per decay, but it's 180. That means it's 90% efficient transition. Gallium, I would not memorize any numbers about gallium, but here's what's worth noting. Anything ending in IUM other than rubidium, but gallium, thallium, and indium, all three of those have half-lives near 3 days. They all decay by electron capture, and they're all and they're all cyclotron produced. So anything ending in IUM, gallium, thallium, and indium, 3-day half-life, cyclotron produced, and electron capture. And you'll note here that there are 3 different energies coming out of gallium. Which ones do we like? We like 94 and 184. 94 is pretty close to the bottom of the ideal range of 100, still pretty good quality. 184 is perfect. It's right in the middle of 100 to 250. What we don't like is 296. So we set our discriminator, our window around these two and collect those. And we simply discriminate out this 296. So look what we've got. We have a total of 64% abundance from these 2 photons. Anything over 50% is considered really good. So gallium has plenty of photons. We don't use it much anymore because we have better agents, but it's been around since 1971, I believe was the approval date for it. Okay, let's go to the next one. On this slide, the 2 that you must know would be the first one and the last one. Iodine-123 has a 13.3 hour half-life. The energy is perfect, 159 keV, just a little higher than technetium. And you'll note the percent abundance is really good, 83%. We go down to the bottom for a moment. We have I-131, 8-day half-life. The way I remember this number is the energy equals the number of days in a year, 365 approximately. And you'll note again, the percent abundance of that particular photon is really good, 82%. Now it turns out that I-131 actually has 19 gammas, but I didn't have room for all of them. But that's what the decay scheme looks like. There are 6 different betas going to 6 different energy levels. And then we have the 14 gammas that I'm showing you here going from many levels to many other levels. Let's go back for a moment. We're going to come back to that. And sandwiched in between these 2 is I-125. Unless you do glow-fill studies for glomerular filtration rate, you may have never seen an I-125 study of any kind. We really don't do them anymore, although many years ago, perhaps 25 years ago, this was the principal isotope for using radioimmunoassays. The tracer was something, for example, like I-125 digoxin for doing a digoxin assay. And we really can't image it at all, except maybe very poorly, because look how low the energies are. The X-rays are, and there are a lot of them, the X-rays are 28 keV, the gamma rays are 35, and between the 2 of these, the abundance is very high. So we have a very large quantity of a very poor energy. Not ideal at all for imaging, but it's a wonderful counting isotope. Now let's go back to this decay scheme. You can see here 14 gammas and 6 betas. So I have a couple of good questions for you. Number 1, which is the numbered gamma that we image with for I-131? Now, if you look way over on the right side, I'm going to give you at least a little hint here. The energy is 0.3644. And there are actually a couple of different gammas that drop down to 0.3644. And there are actually a couple of gammas that drop from 0.3644 down to 0, which is the numbered gamma that we image with. Anybody? So it has to match up from the base of the arrow to the tip of the arrow. It has to be a difference of exactly 0.3644, not even 0.3645. It has to match to 4 decimal places. So if you take a look at gamma 9 goes from here, that's 0.3644, down to 0. So the one we image with is gamma 9. And here's another question. That's your answer. And here's another question that came right off of an old board exam. That decay scheme showed you that there were 6 betas and 14 gammas. Therefore, true or false? You might like true or false questions. You got a 50% chance of getting them right. True or false? 14/20ths of the tissue damage came from the gammas and 6/20ths came from the betas. True or false? Anyone?
False.
Good. It's false for 2 reasons. What's one of them? So which is more damaging, betas or gammas?
The betas are more damaging.
Sure. So we can't assume the factors of 14/20ths or 6/20ths because all you're looking at there is percent abundance, and you're not even considering the LET. We know that the betas are much more damaging, so this is a false assumption for that reason. It's also a false assumption for another reason, which is that you don't know what the percent abundances of those are. But the only way that it could be 14/20ths and 6/20ths is if each of these had a percent abundance of exactly 5%. And actually, none of them does. So here are your answers. The LETs are different. And the percent abundances vary all over the place. Okay. The next list, I think you certainly need to know indium and rubidium. You'll note indium has a half-life of almost 3 days. Excuse me. 67 hours. It has 2 energies that are perfect. 173 and 247 are both within 100 to 250. And look at the percent abundances. Now, that adds up to 183. This is not a positron emitter. We're not looking at 511 keVs at all. So how is this possible? So we're going to jump ahead to the decay scheme, and then we'll come back to this slide. We can see that indium decays to cadmium 111M. What percent of all indium atoms go straight to the ground state and bypass these excited states? The answer is 0. You don't see a line from here down to here. Sorry. And so none of the indium goes straight to ground. 100% goes to this one. Cadmium 111M has 2 excited states. One is highly excited. We'll give it 2 stars. One is excited, and then that one decays to the ground state. So look what we've got. We have sequential decay from here to the intermediate excited state and then to ground. And that gives us a 247, which is, I think, a little over 90% abundant. And then this one is something like 89. Well, I don't recall the exact numbers, 89 and 94. And so we're going to get almost 200 photons from 100 disintegrations. So nuclear physicians actually have a love-hate relationship with indium. They love this. They love getting 183 perfect energies. What they don't love is that indium costs over $100 a millicurie compared to technetium, which is, I don't know, a couple of dollars a millicurie. Let's go down to rubidium for a moment. The shortest half-life that we have ever imaged with ever, other than carbon 11, nitrogen 13, oxygen 15. This is a 75-second half-life. Just looking at this number right here, 511 keV, what would you say would be the mode of decay of rubidium? Just looking at that one number. Anyone? What is 511 keV? It's annihilation radiation. Sorry? Yeah, so this has to be positron decay. Anytime you see a 511 in this column here, that's got to be a positron emitter. And so remember that that could have been 200% abundance, but this is 95% efficient. And so we have 190 photons from 100 disintegrations. Now, molybdenum is in the middle. by coincidence, and not for any good reason, these two happen to have same half-lives. And what's the sole purpose of molybdenum? As you know, we never inject it into patients. Molybdenum is simply what we use as the parent of technetium in the molybdenum technetium generator. And while I don't think you need to know any of these numbers specifically, molybdenum has two very high energy gammas, and that's why it's so difficult to shield. That generator weighs over 48 pounds. 47.9 of those pounds are lead, and the rest of it is a plastic container in the fluid path. So we are really concerned about these big photons here. Yes, the percent abundance is low, but a generator doesn't contain millicuries. It contains curies. Curies, that's a huge amount of radioactivity. And then finally, we have this last slide. Obviously, you must know technetium, 6-hour half-life, 140.5 keV. And you'll just note that the percent abundance is very high, 90%. Also, we have thallium. Remember I mentioned IUM, thallium, 3-day half-life, has two perfectly wonderful gamma rays and a lot of 71 suboptimal X-rays from the Mercury daughter. So look at this. We love those two photons, but the total percent abundance is only 10%. We would have to give 9 times as many millicuries of thallium as we do of technetium to get an equivalent number of photons. But fortunately, there are lots and lots of these Mercury X-rays. I don't know the number, but it's way up there. So we have lots of photons. The problem here is 71 keV is really suboptimal. That is about the lowest you could go and even hope to get a decent image. And as you know, the thallium image will never be able to compete with a technetium image. The quality just will not be there. Finally, we have xenon, 5-day half-life, suboptimal energy, but good enough for us to do a pulmonary ventilation study with. And the percent abundance, you'll notice it's moderate at best. It's on the low side. And so that's one of the reasons that when we give xenon for a ventilation study, we give lots of millicuries. When we're doing a technetium MAA perfusion scan, we typically give 3 millicuries of tech MAA. But for xenon, we give 20 or 30. We have to give a lot for 2 reasons. Number one, the percent abundance is not that high. And number two, what's the T effective of xenon? How long does this stay in the lungs? The effective half-life is measured in seconds, and we know it's clearing out very rapidly, and therefore we have to give a lot. We often give 30 millicuries for a ventilation study. Okay, I think that, yes, that's the last of the slides that show you the constants of diagnostically useful nuclides. This slide, I'm not even going to review it with you, except it's here for your reference. If you ever want to know the numbers here for therapeutic isotopes, and we already saw I-131 previously a couple of slides ago, but for all these isotopes here, P32, samarium-153, strontium-89, and yttrium-90. Here's the one really important thing to remember. P32, strontium, and yttrium-90 are pure beta emitters. They emit no gammas. They pose almost no risk to the dose administrator other than perhaps a hand dose, but there are no gammas coming out. So we don't have to isolate the patient. The patient does not have to be isolated when he's home. P32, strontium, and yttrium, they're great for working with therapeutically. Samarium, which is bound to a bone agent and used for palliation of bone pain, happens to emit a gamma ray of about 100 keV. So you could image that if you wanted to. So you can see the energies vary all over the place. The half-lives are as short as approximately 2 days and as long as 50 days. And the percent abundances also vary. But these three here, P32, strontium, and yttrium, all have 100% abundance. Pretty hard to beat that. And alpha emitter, the only one that's approved today, is radium-223 chloride, which you probably know is the product name of Xofigo, 11-day half-life. Now look at the whopping energy here, almost 6 million electron volts. And we love that. The higher the energy, the better we can do therapy. And anyway, what's the penetrability of an alpha? If you recall from the lecture from last week, we said alpha particles, even these powerful ones, only go micrometers. They can't even penetrate a sheet of paper. So they don't go very far. So they're dumping all of their energy in a very short distance of travel. That implies a very high LET. And radium produces a very high percent abundance of these alpha particles. Okay, now a common exam question, and we're going to cover one of these answers now and the others a little bit later, but a common exam question is the following. Here is a string of isotopes. Are they generator produced? Are they cyclotron produced? Are they nuclear reactor produced? Or are they fission reactor produced? And so here's the first question related to that. What three isotopes that come from the fission process are commonly used in nuclear medicine? Now let's take a very brief look at the fission process. Uranium-235 is called fissile or fissionable material. It undergoes what's called an NF reaction. Now, you recall from last week when we looked at nuclear equations, we always knew what those two things were. We had NP, neutron and proton. We had N alpha, neutron and alpha. F simply means fission products. And there are many of those, 40, 50, 60. There are many of them. So when uranium picks up this neutron, it's converted to uranium-236. It fissions and produces many different nuclides. The atomic mass averages somewhere in the vicinity of 100. Let's call that 90 to 110. And the other fragment is typically 135 on the average. Let's call that 125 to 145. And so here's the answer to your question. Molybdenum, which is 99, is very close to the 100. And iodine and xenon are both in the 130s, you can see here, and that's close to 135. And as I mentioned, there are many, many other isotopes, and there are even many medically valuable isotopes, but not nuclear medically valuable. They're used, for example, in radionuclide therapy for therapy sources, things of that kind. So here's your answer to that first question. Fission-produced nuclides that we're interested in, only those three: molybdenum, iodine, xenon. Now, I don't teach instrumentation. My colleague, Dr. Holloman, does. In the very last two lectures in the series, he's going to be giving you a total of 4 hours that's related to instrumentation. But this question has appeared so often on exams that I want to show it to you now. You may hear it again when he talks. But if you take a look at the gamma ray spectrum of I-125, this is as a function of energy, all of the photons fit in this peak. This peak averages somewhere around 32 or so. The 28 keV X-rays and the 35 keV gamma rays fit in this peak, and we shouldn't be seeing another peak, but we always see it. And the area under this curve compared to the area under this curve has a fixed ratio. It's approximately 3 to 1. I don't know what it exactly is, but this peak has a name. What is it called and why is it there? Now keep in mind, it's an artifact. Nothing is coming out with the energies that this peak reflects. But what is that peak called? Anyone know? Yes?
A sun peak.
Excellent. So here's what's happening. This is called a sun peak. And if two photons, let's say 228s, hit the crystal in the same moment, the crystal, if it's in the same microsecond, the crystal doesn't realize it was two photons, simply sums up the energy. And what does it see? 2 times 28, it sees a 56. 2 times 35, it sees a 70. One of each, it sees a 63. So those are the numbers in the bottom of this paragraph here. And this peak would include the 56, the 63, and the 70. So it looks like I-125 is emitting in this range, but it's not. That's an artifact. However, because the ratio of this to this is fixed, When we set a window to count I-125, we're not going to ever image it, but to count it, we set a window from approximately right here all the way out to right here. And we count all of those photons in that window. So that is a sum peak. In one book that I was reviewing a few years ago, I saw it called a summation peak. You might see that, but I doubt it. Most people refer to it as a sum peak. And keep in mind, it's an artifact. Okay, we're going to delve into units of radioactivity, but before we do so, any questions about anything that we have covered today? If not, then let's take a look at units of radioactivity. The basic unit as defined by the Nuclear Regulatory Commission is in fact the Curie. And there are many Curie-related terms. We're going to look at them on the next slide in a moment, all the way from megacurie down to femtocurie. But let's take a look at the definition. First of all, a curie is not an object. We often talk about a millicurie as an object. The chief tech might say, go in the hot lab and draw up 10 millicuries of technetium, or go bring me 10 millicuries. You can't bring 10 millicuries. It's not an object. It's a decay rate. We talk about it like it's an object, but it's not. A curie is a disintegration rate of 3.7 times 10 to the 10th. And if you multiply it by 60, you could get DPMs, disintegrations per minute, but we're only going to deal with DPS. So let's take a look at all the different units. I've underlined, highlighted in bold, and italicized this one because this is the one you need to know. If you know that a millicurie represents a disintegration rate of 3.7 times 10 to the 7th, you can easily get to any other one in the chart here. There's a difference of a factor of 1,000. A curie is 1,000 millicuries. That goes from 10 to the 7th to 10 to the 10th. A kilocurie is 1,000 curies. That goes from 10 to the 10th to 10 to the 13th. A megacurie, a nuclear power plant term, would be 10 to the 16th. And if we're going the other direction, a microcurie is 1,000th of a millicurie. That drops from 10 to the 7th to 10 to the 4th. Nanocurie, 10 to the 1st. And look how tiny these two are. A picocurie is 2 disintegrations per minute. How do you separate that from background? Background could be almost two disintegrations per minute. It's not easy to do. You have to count for extremely long periods of time under very carefully controlled counting conditions. And look at this one. A femtocurie is 2 times 10 to the minus 3 disintegrations per minute. That means you have to count for 1,000 minutes just to get 2 disintegrations. That is truly difficult to measure a femtocurie. But again, we're going to concentrate on this one. So if you want to memorize the only really important one, the millicurie, which is what we use 99% of the time, is a disintegration rate of 3.7 times 10 to the 7th disintegrations per second. When do we use microcuries? Thyroid uptake test, perhaps. When do we use curies? We eluded the generator. We removed 3 or 4 or 5 curies from the generator. Now, as you know, the tracer level work that we do in nuclear medicine is on the microcurie or the millicurie range. We need a number of microcuries to form an image, but we don't even need 1 microcurie to count a sample, just to get a measurement. For example, if you have a well counter, 1 microcurie or more will flood the detector and cause the dead time to go way up because that's such a sensitive instrument. A gamma camera can handle huge count rates compared to that detector. So we typically work on the microcurie range for things like thyroid uptake and millicurie range for almost everything else. Now, it's very important to understand the difference between a disintegration per minute rate and a count rate. DPMs and CPMs are never, ever equal. A disintegration is an event that took place. We may or may not be able to detect it depending upon how good our detector is. And we don't have a detector, and neither do you, that's over 65% efficient. that's a well counter. You're lucky to have one 65%. So that means that the disintegration rate will never equal the count rate, ever. And so if anyone asks you what's the activity of something, don't ever give it to them in counts per minute, because that's totally invalid. You can only give it to them in disintegrations per minute. And as you know from this slide, if we know disintegrations per minute, we can easily convert it to millicuries. So one count will therefore never represent one disintegration because of crystal inefficiency and also in some cases, suboptimal counting geometry. So how do we define detector efficiency? The detector efficiency is simply the count rate that you got divided by the known disintegration rate of the sample. You'll always know how many millicuries or microcuries it is, times 100%. The only way this could equal 100%, this detector efficiency, is if we had a detector that never missed a photon. We just don't have that. So it's going to be defined as count rate divided by the disintegration rate times 100%. Now, when we work problems with detector efficiency, you can use this efficiency in a problem either of these two ways. Let's say if it's 47%, what does that mean? From 100 disintegrations, you're only going to detect 47 counts. Or if you flip it up this way, you only get 47 counts from 100 disintegrations. Now, think back to the 3rd grade when you were learning how to do dimensional substitution. And your teacher said that 1 foot is how many inches. So you're going to say 1 foot times 12 inches per foot, and you've got your answer. But if you had inches and you wanted to convert it to feet, you would take inches and multiply by 1 foot over 12 inches. So you could use that fraction either like this one, right side up or upside down, because this is an equality. 100 disintegrations equals 47 counts. So you can use these fractions either way, and you'll see examples of that pretty shortly. Okay, now, how would we set up this problem? And it's really a pretty simple problem. This is a recall from an old exam. We have a 1 millicurie standard of cobalt. The count rate is this number here. What is the detector efficiency? So do you know the count rate? Yes. Do you know the disintegration rate? Yes. What is the disintegration rate of this 1 millicurie? By definition, what is it? Anybody? Come on, somebody has to know. Come on. How do we define a millicurie?
3.7 times 10 to the 7th.
Thank you very much. So we simply say the count rate, 2.4 times 10 to the 7th, I gave you that, divided by the disintegration rate, which you should know, 3.7 times 10 to the 7th. 10 to the 7ths cancel. And basically, you've got 2.4 over 3.7. That's 0.64686 multiplied by 100%. And this is an excellent detector with a 65% efficiency. So when you see a problem like this and they don't give you the disintegration rate, don't panic, because if you know millicuries, you can always convert it to DPMs. Okay. Now, this is an important slide because unfortunately for you, the United States works in the millicurie and microcurie and curie systems, but the rest of the world doesn't. They work in becquerels and mostly megabecquerels and gigabecquerels and terabecquerels. And on your board exam, they often ask about becquerels. So I want to make sure you are familiar with the details here. By definition, a BQ is 1 disintegration per second. Now, most people who are knowledgeable about these terms, people in nuclear medicine, hate becquerels. We don't ever deal with something that's 1 disintegration per second. A measly little millicurie is 37 million disintegrations per second. So here's the really important one to highlight. And if you have your lecture notes printed in front of you, I would tell you put a star by this line. The conversion factor from one system to the other is this. 1 millicurie equals 37 megabecquerels. Here's actually where that came from. A millicurie is 3.7 times 10 to the 7th. That's 37 times 10 to the 6th, but 10 to the 6th is million or mega. And so that's where this came from. It's 37 mega or 37 million becquerels or DPS. That's a conversion factor right here. And we're going to use it in a few problems shortly. Now, you all have computers, and you'll recall that 10 years ago, you were so proud of your computer because it had a 1 megabyte hard drive. And now we have gigabyte hard drives. I have a computer at home that has a terabyte hard drive. And so each of those differs by a factor of 1,000. Mega is million, that's 10 to the 6th. A gigabecquerel is a billion, or it's 1,000 times a million. So a gigabecquerel is 1,000 megabecquerels. A terabecquerel is 1,000 gigabecquerels. So it's 1,000 times this. And I think this last one I'm not even going to cover at all. I don't think we need to know what that one is. But this is a really important one right here. 1 millicurie is equal to 37 megabecquerels. Now, let's solve a couple of problems. Let's read the first sentence here. A count rate of 3.7 times 10 to the 7th counts per second was obtained. True or false? That's exactly 1 millicurie. True or false? Who knows?
True.
I think I heard a true and a false. Okay, so here's a hint. Look at the units. Can counts per second be reconciled with millicuries? It cannot. Only disintegrations per second. So that is not a millicurie. It might numerically look like a millicurie, but it's a count rate. And since this detector is only 1/3 efficient, since this looks like 1 millicurie, the answer really has to be 3 millicuries. In other words, the sample contained 3 millicuries, but you only detected the number of counts or disintegrations equivalent to 1 millicurie. Let's look at the math. You won't have trouble following it. I gave you this number, counts per second. Here's that fraction. We know the detector efficiency is this. So we've got times from 100 disintegrations, we get 33 counts. Counts cancel. Times 1 millicurie is this many disintegrations per second. Disintegrations cancel. Seconds cancel. Counts have already canceled. 3.7 times 10 to the 7th conveniently cancels with 3.7 times 10 to the 7th. And what are you left over with? 100 over 33.33 millicuries, which is exactly 3 millicuries. So don't be fooled. If you see 3.7 times 10 to the 7th counts per second, it cannot possibly be a millicurie because we don't have a detector that's 100% efficient. Okay. Number 2. After we read this, I'm going to give you 10 seconds to come up with this answer in your head without a calculator. We have a sample. The disintegration rate is 3.7 times 10 to the 8th becquerels. In your head, how many millicuries is that?
10.
Did you say 10?
Yes.
Perfect. By definition, 1 millicurie is 3.7 times 10 to the 7th. So it would take 10 millicuries to be 3.7 times 10 to the 8th. Here's the math. This many BQs times, by definition, a millicurie is this many BQs. Becquerels cancel. 3.7s cancel. 10 to the 8th divided by 10 to the 7th is 10. Very easy problem. If I got that problem on my board exam, I would say, thank you, Lord, I'm going to get one right, because that is very simple. Let's take a look at this one. This is also, if you know the conversion factor, this won't take you with a calculator 5 seconds to work. We have a sample, 46.34 millicuries in a dose calibrator. How many megabecquerels and gigabecquerels and terabecquerels? So what's our conversion factor? Remember that 1 millicurie is 37 megabecquerels. So let's take a look at the math. We have 46 millicuries times, by definition, there are 37 megabecquerels per millicurie. Millicuries cancel. So we have 1,700 megabecquerels. Now, as we go up to gigabecquerels, we have to move the decimal point 3 places to the left. So 1,700 megabecquerels is 1.7 gigabecquerels. And to go to terabecquerels, again, we have to move this decimal 3 places to the left. So 1.7 gigabecs is 0.0017 of a terabecquerel. Now, these numbers look hugely different. 1,714 and 0.0017, but this and this are exactly equivalent because a terabecquerel is 1,000,000 times as large as a megabecquerel. Okay, you actually might be able to work this in your head also. We have a sample that measures 10 millicuries. What is that? How many DPS is that? If it's 10 millicuries, how many disintegrations per second? Who knows? It's not 1 millicurie, it's 10. 3.7 times
10 to the 8th.
Good. So you know that the disintegration rate is 3.7 times 10 to the 8th, but your detector is only 50% efficient. So how many counts are you going to get? You're going to get half of that number. 10 millicuries times 3.7 times 10 to the 7th. That gives us 3.7 times 10 to the 8th, but it's only 50% efficient. So you're only getting 50 counts from 100 disintegrations. Disintegrations cancel, and you have disintegrations. Sorry, and now you have counts per second per millicurie. This is simply half of this. Half of this, 3.7 times 10 to the 8th, 50% efficient. We take that disintegration rate, cut it in half, we got our answer. It's a working in your head problem, basically. Okay. Number 5. Which one of the following accurately defines a millicurie? A, B, C, or D?
D.
Good. It's got to be disintegrations per second. It has to be either C or D. It can't ever be in terms of counts. But by definition, it's disintegrations per second. So choice D is certainly correct. Now, related to all of that is a term that's called specific activity. What it does is it gives you a sense of the radionuclide purity. If you have iodine 131, for example, and it's carrier-free means there are no other iodine isotopes present. There's no I-130, 129, 128, 132, 133, 134. They're all absent. It's ultra pure. So specific activity, if it's ultra pure and carrier-free, will be a very high number. But most isotopes have things that contaminate them a little bit. You might, for example, have I-131 contaminated with I-129, which is naturally occurring. That would lower the specific activity. So here's how we define specific activity, is the activity of that nuclide per mass of that isotope. For example, the activity might be a certain number of millicuries, and the mass of the isotope might be nanograms or micrograms, or it even could be moles or grams. So we have A over M, activity over mass, and it must be in terms of either millicuries or a millicurie term or disintegrations. Those two we can convert one to the other, and it has to be in a gram term like milligrams, micrograms, kilograms, or a mole term. Those of you who've had chemistry will recognize the word mole. So here's a problem right off an exam. Which one of the following is not specific activity? Now, all you want to know is this an activity over the mass? The first one, activity over mass, that's millicuries, yes. Milligrams, that's mass, yes. How about this one? Kilocuries, that's an activity. Micromoles, that's a mass. How about this one though? Counts per minute per millimole. Could that possibly be specific activity? Yes or no?
No.
No, because counts per minute, you don't know the detector efficiency. Therefore, you don't know the number of disintegrations per millimole. So the answer to this question, the answer to this question, which could not be an example, would in fact be this one. DPS per gram, that's fine. Disintegrations per second, we can convert that to millicuries. Gram is a mass term. So the correct answer was counts per minute per millimole. That's the one that could never be specific activity. Here's one more. Which of the following is our examples of specific activity? Let's go down the list and just say yes or no. Milligrams per curie.
No.
Yes? That's correct. No. The real answer is no. But if you took this and took the reciprocal of it and converted it to curies per milligrams, that would be okay. But not in this format. This is mass over activity. That's wrong. How about this one? Curies per micromole. Is that a good one?
Yes.
Yes, for sure. Activity over mass. How about this one? Counts per millimole. Is that good or not?
No.
That is not good. Counts are never activity. So the only correct answer here is choice B, which is counts per micromole. Okay, let's take a mental break. Any questions about anything that we have covered? Anybody? Okay, before we start this, we're going to spend the rest of our time today working a lot of math problems. We're going to be dealing with first radioactive decay, and I'm going to teach you an entirely new way of working these problems where you don't have to use natural logs, e to the minus lambda t. You don't have something that no human can understand. It's not logical to us that e to the minus lambda t is the fraction remaining. We humans don't think in terms of negative natural logs. We are more linear thinkers. And so you'll see in the equations that we're going to deal with that we'll have a totally different and much simpler way to work these problems. Now, before we do so, if you'll take out your scientific calculators or your cell phone, if that's where you have it, on your cell phone, let's see if I have this in here. On your cell phone, there is a key. We may have used it last week, I can't recall. That's either X to the Y or Y to the X, or there's a little caret symbol. It looks like an inverted V that looks like this. All of three of those mean to the power of. So anyone having difficulty finding that key on the calculator? If not, then I'll assume everyone has found it. And let's take a look here first at the definition. As I'm sure you know, decay is exponential. It's not linear. If we have 100 millicuries and go through 2 half-lives, it doesn't go from 100 to 50 to 0. We know it doesn't do that. That would be linear. Nothing related to radiation is linear. It's all exponential. So we know that it goes from 100 to 50 to 25 to 12.5 to 6.25 to 3.125 and so on. So decay is exponential, and we describe it in terms of the half-life. That's the T physical, and we spent a lot of time on that last week, but I'll define it for you again. The period of time that it takes for half of the parent to decay to the daughter, and all of this has to do with nuclear rearrangement and nothing whatsoever to do with electrons in electronic orbitals. This is all a nuclear rearrangement based on the fact that the nuclide is unstable. It might be very unstable and have a short half-life, or just slightly unstable and have a very long half-life, but it has to be unstable. So again, exponential and defined in terms of the half-life. Now, there are three terms that define any isotope. If you will tell me The mode of decay, that's a type of emission. Is it alpha, beta, gamma? The energy, how many keVs, and the physical half-life. I could look up in a book and I could tell you what that isotope is. For example, if you said it decays by gamma emission, the energy is 140.5 keV, and the physical half-life is 6 hours, that defines technetium-99m. There are 2,850 known nuclides. None of the others has those three properties. We know that would have to be technetium. Now, working half-life problems is simple. We could teach a 10-year-old the basic principles, because if you can divide by 2, you can often answer questions related to this. We go from all of it to a half of it, to a fourth of it, to an eighth, to a 16th, to a 32nd, to a 64th, and so on. What makes decay calculations difficult is that we don't always have a whole number of half-lives. We know, for example, if we have 3 half-lives, we have 1/8 remaining. But what if we have 3.5 half-lives? You can't interpolate. You can't linearly figure out what that is. You need a calculator, or in the good old days, we used to use slide rules or logarithm tables. But today you need your calculator. So let's take a look. We know we're going from 1/2 to 1/4 to 1/8. And that's going what we call prospectively in time. We're going forward in time. We go from all of it to a half, to a fourth, to an eighth. But what about going retrospectively in time? If we have so much now, how much did we have 1 half-life ago? Twice as much. 2 half-lives ago, 4 times as much. 3 half-lives ago, 8 times as much, and 16, and 32, and 64. So we're either going 1/2, 1/4, 1/8, or times 2, times 4, times 8. Now, I'm going to show you a graph, and I think this says it all. From 0 half-lives that have elapsed, if you follow this part of the curve down here, we go from all of it to a half, a fourth, an eighth, 16th, and 32nd, and going retrospectively, going backward in time for -1 half-life, we're going to double it and quadruple it and octuple it and multiply by 16 and 32 and 64. So I think this graph is very, very helpful to understand how radioactive decay works. And since I'm quite sure you understand and follow that graph, when we work on attenuation of radiation with absorbers in probably the next half hour, you're going to see exactly the same graph, except this is going to say log of I for intensity instead of A for activity. And this is going to say half value layers instead of half-lives. But you're going to see the exact same graph all over again. Now, there are 2 ways to plot decay. You can plot it on linear paper like this, where time is linear. Sorry, time is always linear. The activity here is linear, but this is semi-logarithmic paper, where the vertical axis, the activity, is logarithmic, but here time is linear. And so what happens on linear paper is you get a curve, but on log paper, because it's a logarithmic function, you get a totally straight line. Now, both of these will give you the correct value. If you wanted to find the half-life of this, you would go up here and say, okay, this is 100%. I'm going to come right down to the middle. Here's 50% over to the curve, drop a vertical to here, and that'll be your half-life. And here, you're going to do the same thing, but you're going to say this is 100%. 50% will no longer be in the middle. It'll be a little bit higher. Like here, you're going to go over to the curve, drop down, and you're going to get the correct answer. These are going to give you, reading off the curve, they'll both give you exactly the correct values. But which is the better way to plot decay? Log paper or linear paper? What's the best way? What kind of function is it? It's a logarithmic function. It only makes sense to plot it on log paper. This is not wrong, but it's sort of like this is a professional way to do it and this is the amateur way to do it. Neither one is wrong, but this is the more appropriate way. True or false? Parallel lines on a decay curve have the same half-life. True or false?
True.
totally true. And we're going to prove it graphically in just a moment. What we have here, though, is here's a hot sample up here, and here's a cooler sample up here. But I think you will agree that the change in activity as a function of time is the same. The slopes of the lines are the same. The change in activity as a function of time is the same. That means lambda, the decay constant, has to be the same. Here it is, dA dt. Slope of the line is the same. They have the same slope. They have the same lambda. And therefore, they have to have exactly the same half-life. And the reason I asked you this question is that when we get back into studying about generators, and in particular into transient equilibrium, we're going to see that there are parallel lines for the parent and daughter, implying that the half-lives are the same. So, excuse me, very important to note that parallel lines mean they do have the same half-life. Now, let's see if you can help me to solve this problem. And we're going to prove graphically that those have the same half-life. We're up here at 10,000 at time 0. Now, you'll note, by the way, look at the scale. Going from 10,000 to 9 to 8 to 7 to 6 to 5 to 4, you'll see the gaps get bigger and bigger and bigger as we go down. That's because it's logarithmic and not linear. If this were linear, 10,000, 9, 8, 7, 6, 5, 4, 3, 2, 1 would be spaced equally. So now we're up here at 10,000. What would be the half-life of this top curve here? If this is 10,000, we're going to go down to what? 5,000. We're going to go over to the curve, drop a vertical down, and that gives us 5 days. How about this one? At time 0, we're at 5,000. What are we going down to? 2,500. We go over to the curve, and this reads 5 days. So there's graphical analytical proof that they have exactly the same half-life. Now, if you get on your board exam a graph and they ask you to calculate the half-life graphically, that's how we do it. You find your time 0 count, divide it in half, go over to the curve and drop your vertical, and there's your answer. You should hope to get that question. I think it would be very simple. Now, this is where it gets a little bit more difficult. I'm going to briefly talk about e to the minus lambda t, because that is a time-honored equation. You should recognize it. You might see it on your board exam. You have to know what the terms mean. So let's look at what this is telling you. The final activity at time t equals the initial activity at time 0 times e to the minus lambda t. Now this t here is the elapsed time. I don't even see the half-life in that equation. Is it in there or not? Is half-life?
Yes.
Sure it is. Where is it, Connor?
In the lambda?
Sure. What is lambda? By definition, 0.693 over the T1 half. It's in there. It's not evident, but it's really in there. So this is what each of the terms mean. Final activity, time 0 activity, lambda is the decay constant, 0.693 over T1 half, and the T is elapsed time. Don't think that T is the half-life. You're guaranteed failure if you do. Now, if we take this equation and solve it for e to the minus lambda t, e to the minus lambda t is going to be AT divided by A0. Here it is. And what is AT over A0? The final activity divided by the initial activity is the fraction remaining. Now, again, it's not intuitive to us that e to the minus lambda t is the fraction remaining. We don't think in terms of negative natural logs. You could look at this for the rest of your life and it would never imply fraction remaining. But here we have proved that it is. And we want to remember for a moment or two that e to the minus lambda t is the fraction remaining, because I'm going to show you a much more logical, easy to understand, much simpler way to work decay problems. When we're all done, if you like working with e to the minus lambda t and you prefer not to use my method, be my guest. I won't be insulted at all. But at least I want you to see it and give it a try, and I think you'll like how it works. The logic is simple. Here's a little chart I made up for you. By definition, after one half-life, we have 1/2 remaining. After 2 half-lives, we have 1/2 squared, or 1/4 remaining. After 3 half-lives, we have 1/2 to the 3rd power, or 1/8. After 5 half-lives, we have 1/2 to the 5th. That's 1/32. After 8 half-lives, we have a 1/2 to the 8th. I believe that's 1/100, 120, maybe, yeah, 1/256, I believe it is. Doesn't matter what that is. So after n half-lives, even if we don't know what n is, look at the trend here. It's going to be 1/2 to the power of the number of half-lives. So all you need to determine for fraction remaining is 1/2 to the n. That's all. That is what's going into every decay problem. And every one of us understands that the fraction remaining is 1/2 to the n. We take 1/2 and multiply it by itself n times. If n is 3, there are 3 half-lives. 1/2 times 1/2 times 1/2 is 1/8. So we now proved that the fraction remaining equals e to the minus lambda t, but the fraction remaining also equals 1/2 to the n. So since these two are equal, let's substitute 1/2 to the n, which we all understand, 1/2 taken by itself n times. We're going to substitute that for e to the minus lambda t, and look what you get. A is a0 times 1/2 to the n. That is the entire decay equation that you need to know. Now, we have to define n, however, and n is not the half-life. N is the number of half-lives. That's what goes up here. And n might be a whole number, and it might be 9.427. We don't care what it is because the calculator doesn't care what it is. So let's define n. N is the number of half-lives that we have, and we simply take the t elapsed divided by the half-life. For example, if I ask you the following, in one day, how many half-lives of technetium have elapsed in one day? How many? Who's got it?
4.
Good. You took the elapsed time, 24 hours, divided by the t1/2, 6 hours, you came up with n. So you can see that this is correct. The number of half-lives is t elapsed over t1/2. So if we take this term here and substitute it for n, look what we've got. Final activity equals initial times 1/2. This is, for some reason, in the wrong place. It should be moved farther to the right, but this is all the exponent. Parenthesis, t elapsed divided by t1/2, close parenthesis. Let's see if it, looks better here. So there is no half-life problem anyone can give you that you cannot solve with this equation. All you need to have is the y to the x key and the parenthesis key. That's all you need. You're going to punch in this number, the activity, times 0.5. Right here goes the y to the x key to the power of parenthesis, t elapsed divided by t1/2, close parenthesis, and you're going to punch equals, and you're done. So let's take a look at let's take a look first at retrospective decay with the same kind of formula, and then we're going to work some problems. Going backward in time, what happens? Every half-life in reverse, we double it. 1 half-life ago, we had twice as much. 2 half-lives ago, we had 4 times as much. 3 half-lives ago, 8 times as much. So very simply put, n half-lives ago, we're going to have 2 to the n times as much. 10 half-lives ago, we would have 2 to the 10th power times what we have at times 0. So look at this equation. Makes sense, right? Final equals initial times 2 to the power of n. If you know n, simply going to be n. If you don't know n, t elapsed over t1/2. Okay, now I think you'll agree that 1/2 to the n is a really simple way to work this as opposed to e to the minus lambda t. But we're going to have some practice right now. Now, before I work any decay problem, I like to estimate, make a linear guess at the answer. And then, and because my linear guess is almost guaranteed to be within 10%, if I come with an answer not within 10%, I know I calculated it wrong. My answer's out in left field somewhere. Well, let's take a look. For technetium, we know it's a 6-hour half-life. we have 100 millicuries. What will be the activity in 3 hours? How many half-lives have elapsed? How many half-lives in 3 hours?
You're
Half of a half-life, right? So let's do a mental calculation. Time 0, we have 100. 1 half-life, we have 50. Our linear guess is for half of a half-life, we have 75. Here's 2 things we know. We know it's going to be wrong. It won't be 75, but we know it's going to be very close to that. Now, here are your keystrokes. Here's your setup. We have 100 millicuries times 0.5 to the power of, in parentheses, 3/6. Now, I'd like you to try these keystrokes, every one of these problems, try these keystrokes so you can get used to working this. Punch in 100 times 0.5, then hit whatever key you've got on your calculator, X to the Y, Y to the X, or the caret symbol. Punch in the left-hand parenthesis, 3 divided by 6, punch in the right-hand parenthesis, and you must punch equals, and you should have come up with 70.71. Now, because you know that the value of this is 1/2, you didn't really have to go through all this. You could have said 100 times 0.5, Y to the X key, 0.5. You know how many half-lives it is. Remember, it's 1/2, sorry, it's going to be 1/2 to the n. If n is 0.5, it's going to be 100 times 0.5 to the power of 0.5. Okay, so there are your keystrokes. Everybody got that okay? Any questions? I think it's a much simpler way than doing it the other way. Let's work a couple more problems. This is a problem that nuclear medtechs have to do every single day on, or at least used to every single day on every dose of every product of every isotope. You made a product at a certain point in time, 7 a.m. for example, but now it's 9:45 a.m. The activity, which was originally 75 millicuries per milliliter, has decayed. It's a different value. It's going to be less. We can even take a linear guess. This is 3 3/4 hours for technetium. It's going to be a little over 1/2 of a half-life. So I would say that if it started out 75, it's probably going to be around 40 or 50, somewhere near half of that value. But let's take a look. And by the way, our computers are doing this for us. Nobody has to look up these values on decay charts anymore. But let's take a look at this and look what the problem is asking. What volume do we have to draw at 9:45 a.m. to get 25 millicuries? Now, if we drew 1 milliliter right now at 7 a.m., we would get 75 millicuries. We don't want 75. We want 1/3 of that. So if you drew the dose at 7 a.m. and drew 1/3 of a milliliter, you would get 25, and that would be great. But it's not 7 a.m. It's 9:45. So let's take a look. Here's the setup. A0, we have 75 millicuries per milliliter times 1/2 to the power of 2.75 hours. Was that correct? Yes. 2 hours and 45 minutes, 2.75. That's actually a little bit less than a half-life, so it's got to be our guess needs to be a little bit more than 50, divided by 6. And if you crunch through these numbers, here are your keystrokes. Please give them a try. 75 times 0.5, Y to the X key, open your parenthesis, 2.75 divided by 6, close your parenthesis, and you must punch equals. If you don't punch equals, what's in the display is simply the value of that fraction. When you punch equals, here's what you get. 54.6 millicuries per milliliter. Our linear guess was a little bit more than 50, so we're good. So what does this mean? If we draw 1 milliliter at 9:45 a.m., we're going to get 54.6 millicuries. We don't want that. We only want 25. We basically want 25 54ths of a millicurie. And look how nicely the units cancel. Our volume is going to be 25 millicuries divided by this term, 54.6 millicuries per milliliter. Millicuries cancel. Milliliter is in the denominator of the denominator, and it flips up here. Our volume is 0.46 of a milliliter. That is, unfortunately for you, a two-part problem, but it's not really very hard. And I think these keystrokes make it much easier. Okay, anyone have any keystroke difficulties? Any questions? Okay, if not, let's take a look at this problem. Now, you could solve this problem graphically, and also you can solve it mathematically. And the math is really pretty difficult. And but first thing we're going to do is take a linear guess. Time zero, it's 20,000. 14 hours later, it dropped down to 14,500. Now, 14,500 is roughly halfway between 20,000 and 10,000. If it were one half-life, it would have gone from 20,000 to 10,000, but it didn't get that far. It's somewhere right in the middle. So again, we're going to say that 14,500 is about half of a half-life. So here's our linear guess. 14 hours is half of a half-life. 28 hours is a whole half-life. That's going to be our linear guess, 28. Now, I'm going to skip this because I don't think you're going to get this kind of problem on your exam, but let's take a look. You can see what the calculation came out to be, 30.2 hours. Our linear guess was pretty good, but let's take a look at the graphic solution here. We're at 20,000. There's our 0.1. This yellow dot here is at 14,500. And I've extended the line down for you. And so here we're going to go from 20,000, that's A0, to 10,000. This dotted line takes us to the curve. We drop a vertical down and we're getting 30 hours. So that simply corroborates the fact that that is a correct answer. So if we have time at the very end, I may come back to problem 3, but for right now, I'm going to skip it. It involves taking the exponent of a fraction and taking logs, and I think you're not going to get that problem. All right, true or false? After half of a half-life, 75% of the initial activity remains. True or false? We actually worked that in problem number 1. That's false. How do we know it's false? Because that's a linear extrapolation, right? Half of a half-life, you said, okay, 75% is halfway between 50 and 100. So that sounds logical, but it's only logical linearly, not logarithmically. And here's how to prove it. You got a half of a half-life, right? 0.5 to the power of 0.5 equals 0.7071, okay? So this said, after half of a half-life, n equals 0.5. On your calculator, give this a try. 0.5, y to the x key, 0.5 equals. And so it's 70.71% remaining, or fraction is 0.7071. And it's very close to our linear guess of 75, but not exactly. Okay, now this is a little bit more complicated problem because you have to know something about how to calculate T effective. And this, in fact, is one of those special cases we reviewed last Thursday. Assume that the biological half-life of xenon in the lungs is 15 seconds. Now, we know that xenon has a 5-day physical half-life. That's much, much, much longer than 15 seconds. So in that extreme case, T effective is going to be equal to 15 seconds. Okay, everybody following okay? T effective is 15 seconds. It didn't matter if xenon was 5 days or 5 hours or 5 weeks. This study is over in 2 or 3 minutes. So T effective is 15 seconds. Great. Question says, what will be the activity in the lungs 1 minute after inhalation of 15 millicuries of xenon? So we have an elapsed time of 1 minute. We have a T effective of 15 seconds. So how many T effectives would 1 minute be? If the T effective is 15 seconds, but the elapsed time is 60 seconds, how many T effectives would that be?
4.
4.
Sure, exactly. So let's take a look at the solution. Since T biological is 15 seconds and T physical is so long, T effective is 15 seconds. Therefore, 1 minute is 4 T effectives. And you could count this on your fingers after 4 half-lives. How much remains? 1/2, 1/4, 1/8, 1/16 of 15 is 15 sixteenths, but 1/16 also is 0.5 y to the x key 4, 0.0625. That is exactly 1/16. You simply take your initial activity and multiply it by 0.0625 or divide it by 16, and you come up with 0.94 of a millicurie. So that's a little bit more difficult problem. To me, the hardest thing there is knowing that the physical half-life of xenon was so long that T effective equals T biological. Once you've got that, it's pretty easy. You know T effective is 15 seconds. 1 minute is 4 of those. 1/16 or 0.0625 remains, and you end up with this. Now, let's take this one step further. This is a work it in your head problem now. We worked that problem just now where we had T effective was 15 seconds. Therefore, there were 4 half-lives in 1 minute. But look at this. What if T effective had been 20 seconds? Okay. Then how many half-lives would have elapsed? Only 3, not 4, but only 3. What is this value here going to be? Anybody? Is it going to be half this number or double this number? Remember, here, you've only got 3 half-lives in a minute. Here, you went through 4. Here, you only have 3.
You're going to double it.
It's going to what? What's this?
Double.
It's going to double, right? This is going to be 1.88. And what about this case? If the T effective had been 30 seconds, where there are only 2 half-lives in a minute, then what happens here?
3.76.
It's going to double again, right? Good. There you go. So as you go from 4 half-lives to 3 to 2, every time you reduce 1 half-life, you're going to double it. 0.94, 1.88, double again, 3.76. And you did not need a calculator to figure that out. Okay. Problem number 6. You should be able to set this up in your head, truly. Across the world, it's a radiation safety standard that people hold radioactive waste for 10 half-lives before they discard it in a waste bin. What's magic about 10 half-lives? What fraction of the original activity remains? Now, you got 10 fingers, you got 10 half-lives, so you could say a half, fourth, eighth, 16th, 32nd, 64th, 128th, 1/256, 1/512, 1/1024. So it's a little bit less than 1,000th remaining. That means 99.9% is gone, and that's why we can throw it away. The residual activity is not even 1/10 of 1%. But let's look at the math. What would we say? What is n? N is 10 half-lives. The answer is simply going to be 1/2 to the power of 10. 0.5 to the power of 10. Try this on your calculator. You're going to get 0.5 y to the x key 10 equals, and here's what it's going to give you, 0.000976. If you round that off, that rounds off to 0.001. That's 1 in 1,000th. And actually, technically, it's 1/1024 if you count on your fingers. But using the math, 0.000976. So that means even less than 1/1000th is remaining. And that's why we can dump it in the waste. Again, every half-life problem, it's simply going to involve 1/2 to the n, 0.5 to the power of n equals. Okay. Now, let's take that one step further. We're going to round off that that 1 over 1,024 to 1 over 1,000. We know it's slightly wrong, but just work this math and in our heads, we're going to round it off. Let's say that 10 half-lives elapsed. The fraction remaining is 1/1000th. We just calculated that. How about 10 more half-lives? What's that going to do to it? Every 10 half-lives reduces it by a factor of 1,000. Therefore, what fraction is going to be remaining here after 20 half-lives? So look, if every 10 half-lives reduces it by 1,000th, then another 10 here is going to be 1,000th of 1,000th, which is a millionth. 10 more will be 1,000th of a millionth, which is a billionth. And 40 half-lives would be 1,000th of a billionth, which would be a trillionth. Now, if you were to do this on your calculator and punch in 0.5 to the power of 40, you would not get exactly this number. You get a number a little bit smaller than that, but I think you get the point. Every 10 half-lives cuts it by a factor of 1,000 again. So we're going from 1,000th to a millionth to a billionth to a trillionth. Okay? Now, everything we've talked about in the first 6 problems has been prospective decay, going forward in time. Let's take a look at a retrospective decay. And I'm not giving you the half-life here because I assume that you know it. A sample of I-131 has an activity right now of 10 millicuries. What was the activity 40 days ago? Okay, for I-131, half-life is 8 days. How many half-lives going backwards would this be? If it's 8-day half-life, we've gone back 40 days. How many half-lives is that?
5.
5, good. So now if you put up your 5 fingers, you can say, okay, you're going to double it, quadruple it, octuple it, times 16 times 32. 2 to the 5th is 32. Here's the math. Fraction remaining, you're going to start with your 10 millicuries and multiply it by 2 to the 5th. That's going to give you 10 times 32, 320. That's how easy this is. This was a particularly easy one because it was exactly 5 half-lives. It wasn't 5.6 or some oddball number, but exactly 5 half-lives. And you could work that in your head. 2 to the 5th is 2 times 2 times 2 times 2 times 2 is 32 times 10. Pretty simple problem. Number 8. The decay constant of an isotope is 0.0693 hour to the -1. The original activity is 100 millicuries. What would be the activity after 10 hours of decay? Now, if I first looked at that problem, I would say, that's 0.0693, and lambda has in it 0.693. I think somebody's probably going to cancel. But what don't we know here? We know lambda, but what we don't know is the half-life. So first, we have to calculate the half-life, and here's how we would do that. Lambda is 0.693 over the half-life. Therefore, the half-life is 0.693 over lambda. That's 0.693 divided 0.0693. An hour to the -1 in the denominator flips up as hours. And this goes into this 10 times. Pretty easy math. So the half-life is 10 hours. If you go back to the problem, the activity had 10 hours of decay. That's exactly 1 half-life. Half of 100 is 50. Pretty easy problem. First, we took lambda, converted it to the half-life. How many half-lives did we have? We had 1 half-life. Therefore, we're going to take our original activity and cut it in half. Okay. Problem number 9. This is a recall from an exam. It was not on a technologist exam. It's actually on a physician's exam, but you should be able to work this just fine. Bi-exponential decay means it's the decay of a mixture of 2 isotopes. So here's one of them decaying very rapidly, this black line over here. And here's another one decaying much more slowly. And we're going to work this graphically, but we're never going to use this curved part here, this gold colored part. We never use that because that's where they interact with each other. So we're only going to, here, we're assuming that this is decaying by this, and we're assuming the other one's not even present. Now, look what the question says. What are the isotopes? One of these you're going to know, and one you probably won't. But let's do this graphically. Here we're at 10. We're going down to 5, over the curve, and this is the 4th line over. That would be 8 days. What would that isotope be?
I-131.
I-131.
Good. And here, now we have this line. There, we could work it from here, but the smart thing to do is take this line as a straight line and just extend it back to times 0. And fortunately for us, that ended up at 3. Half of 3 is 1.5. We go over to the curve and drop down a vertical 60 days. And you might not know that one, but that happens to be I-125. And these boxes I've drawn show you how we calculated. 5, we went from 10 to 5 over the curve, drop down 8 days. Here, we went over to the curve, drop down 60 days. They would never give you a 60-day problem today because we almost never use I-125 for anything. But this was so many years ago that I-125 was commonly used, and that's why that problem appeared. Okay, a couple more problems, and then we're going to take a look at attenuation and hopefully inverse square law. A vial contains a mixture of 20 millicuries of I-124. Half-life is 4 days. And it contains 6 millicuries of I-131. Half-life is 8 days. What will be the activity in the vial 8 days from now? Again, a recall from an old exam. You do not need a calculator for this. You could use one, but you don't need it. You have 20 millicuries. The half-life is 4 days. The decay time is 8 days. How many half-lives have elapsed for I-124?
2.
2. Therefore, 1/4 is going to remain. 1/4 of 20 is 5. Let's remember the 5 for a moment. Here we've got 6 millicuries of I-131, 8-day half-life, 8-day decay time. We have 1 half-life elapsed. Half of 6 is 3. So we had 5 from here and 3 from here, which is 8. And here's the math. 20 millicuries times 0.5 to the power of 2 plus 6 millicuries times 0.5 to the power of 1 will give you 8 millicuries. Pretty easy problem. How about this one? I like to call this a pattern recognition problem. You should be able to work this with no calculator whatsoever. Now, let's mentally decay 100 down. And look at the numbers we're going to get. 100, 50, 25, 12.5, 6.25, 3.125, and so on. So 62.5 should look like one of those numbers. So if you work this in your head, you would say, okay, let's start at 1,000. The first half-life will take us to 500, 250, 125, 62.5. So we, in our head, calculated that that's going to be exactly 4 half-lives. Now, we could work it out with logarithms, and it's not very simple to do, but it'll give you exactly 4. That's, again, one of those tough problems I don't think they're going to give you, but this came off of a resonance exam, could easily be a technologist exam. And this is pattern recognition because 62.5 is one of the even dividends of a 1,000. 1,000, 500, 250, 125, 62.5. So that's going to have the answer of 4. And there it is. Okay. This is probably the last decay problem. For technetium, what fraction remains after 19 hours? A or B or C or D? Who's got it?
D.
D. D like David. Sure. It's 1/2 to the power of elapsed time over half-life. 0.5 to the power of, in parentheses, 19/6. You must use a parenthesis. I don't know what that is, but it's a little over 3 half-lives. So it has to be a little bit of a little bit less than 1/8. Okay, and that's the right answer. 0.5 to the power of the number of half-lives, 0.5 to the power of, in parentheses, 19/6. Okay. Any questions about decay? Anyone? About the math, the keystrokes, anything? Okay, somewhere along the line, excuse me, I'm going to be giving you some worksheets for a homework assignment. It'll probably be much later in the course because we're going to review them on the very, very last day. But if you followed all of that okay, you're going to love attenuation because the concept mathematically is identical. Look how close this slide is to the first slide I showed you. What did that first slide say? Decay is exponential. It's described in terms of the half-life. Here, attenuation, absorption of radiation is exponential, and it's described in terms of the half-value layer. We define that as the thickness of an absorber that is able to reduce the intensity of a beam to 1/2 of its original value, okay? The absorber, the intensity is reduced to 1/2 of its initial value. That is 1/2 value layer. And once we know N, how many half-value layers we have, we no longer care about the thickness of the composition or the absorber. Is it lead or aluminum? We don't care if we know N. If it's 1 centimeter thick or 2 millimeters, again, we don't care. Just like with half-life, all we really cared about is what's N? How many half-lives have elapsed? N. That's the number we need, 1/2 to the N. Now, I think I have it here, but I'm going to, hopefully you can see my hands. I want to just do a quick demo here. The half-value layer of air for technetium is probably, I can't put my hands apart that far. It might be, I don't know, might be 5 meters of air. I don't know what it is. Air has a very long distance. The half-value layer is very thick. But as we move thinner and thinner, let's say we have a pile of cotton balls. That's going to have a certain half-value layer. And then maybe we have a pile of dirty laundry that's dry and a pile of wet laundry. And then maybe we have balsa wood and pine and oak. And then we have aluminum and copper and lead. Now that thickness varied from meters to 0.2 of a millimeter. But once we know N, we simply do not care what the material is made out of. Now let's see if you've got the concept here. Which stops more technetium energy? A half-value layer of lead or a half-value layer of aluminum? Who's got it?
Is it the same?
They are, in fact, the same. Which weighs more, a pound of lead or a pound of aluminum? This is
They weigh the same.
Same, right? A pound is a pound. A half-value layer is a half-value layer. The lead's going to be 0.2 of a millimeter, and the aluminum might be 2-3 centimeters, but we don't care. Once we know how many we've got, that's all we care about. Now, here's what we're looking at. We have a monochromatic source. Monochromatic, for our purposes, as the slide indicates, means that it's monoenergetic. And an example of that would be technetium, where all of the energy is 140.5 keV, or I-123, where all of it's 159. So we have a technetium source going through some barriers. And for a monochromatic source, barrier 1 is equally thick as barrier 2, 3, 4, 5, 6, 7, 8, 9, 10. Every layer in a monochromatic beam is identical. Polychromatic beam, not true at all. We'll deal with that near the end of this. So here we have all these barriers, and here's our detector. And because there are barriers in place, the reading of the source will always be larger than the reading at the detector. Now, this slide should look very familiar to you. Before it said 1 half-life. After 1 half-life, how much do we have left? We have 1/2. After 2 half-lives, we have 1/4. Same thing is true here. As we go from 1 to 2 to 3 half-value layers, we go from a half to a fourth to an eighth to a 16th to a 32nd to a 64th. And as we take out half value layers, that should be on this slide, every time we take a layer out, we double it. Take out 2 layers, quadruple it. Take out 3 layers, octuple it. So here, absorption is only dependent upon n, the number of layers, not the composition. And that's, of course, true whether you're putting them in or taking them out. Oh, I see an error in this slide. I'm not going to fix it now. This A should be an I. It should be intensity. Apologize for that, but that should be intensity. Identical curve that you saw before. We're right here with 0 half value layers. As we put in 1, 2, 3, 4, and 5, we go from all of it to a half, to a fourth, to an eighth, a 16th. The reading drops to a 32nd. As we take layers out, that's equivalent to going backward in time for a half-life. We are going to go from -1 to -2 to -3, -4. We're going to double the reading, quadruple, octuple, times 16, times 32. Exactly identical conceptually to half-lives. Okay. Did you have a question? Someone had a question? No? Okay. Now, this equation is the shielding formula equation. Final reading equals initial reading times e to the minus mu x, just like activity equals activity 0 times e to the minus lambda t. The format of this is e to the minus constant variable. Mu is the linear absorption coefficient. That's a constant. This is the thickness, which is the variable, just like we had lambda was the constant, the decay constant, and the t was the elapsed time. So just like for the half-life equations, look what we've got. Mu, just like lambda, same formula, 0.693 over T1/2, but this T1/2 is the half thickness, which we prefer to call the half value layer. So mu is 0.693 over T1/2, or if you rearrange this, T1/2 would be 0.693 over lambda, over mu. Now, if we solve here for e to the minus mu x, just like we did for e to the minus lambda t, this is going to be I over I0. What is I over I0? It's the fraction remaining, but since it's a beam, we prefer to call it the fraction of the beam that can penetrate the absorbers. So the fraction penetrating will be e to the minus mu x. Now I'm going to use the same words I used half an hour ago. It is not intuitive to us that this is fraction penetrating. We don't think in terms of those negative natural logs. We're accepting that it's correct because we just proved that I over I0, which is fraction penetrating, equals this, but it's just not intuitive at all. Now, we're going to make the same argument we made for half-life. As you go from 1 to 2 to 5 to 8 half value layers, the fraction penetrating will be 1/2, 1/4, 1/2 to the 5th, that's 1 over 32, 1/2 to the 8th, that's 1 over 256, and so on. And just by extrapolation, all we did is took this number here, put it in the exponent. So n, the number of half value layers, the formula would simply be 1/2 to the n, no matter what n is. If it's 10 half value layers, the fraction penetrating is going to be 1/2 to the 10th. So let's go back here, just like before. We just proved that the fraction penetrating equals this. It also equals this. So here it is. These two are equal. Let's substitute 1/2 to the n for e to the minus mu x, and look what you get. I is I0 times 1/2 to the n. Identical in format and concept to a equals A0 times 1/2 to the n. The only difference here is this is a number of HVLs. And with the activity equation, of course, it was a number of half-lives. And so how do we define n? The number of half-value layers is the thickness over HVL. My computer desk here is 4 centimeters thick. But if the thickness of that wood for technetium, the HVL, is only 1 centimeter. The thickness is 4, but an HVL is only 1 centimeter. How many HVLs do I have? I'm going to have 4, right? The thickness divided by HVL. So we simply take this fraction here, plug it in for n, and look what we come up with. Final equals initial reading times 1/2 to the power of, in parenthesis, n. Or if you don't know n, the thickness over HVL. And I can guarantee you there's no HVL problem that you cannot solve with that equation. Okay, now, before we talk about TVLs, any questions so far? Anyone? All right. Fortunately for you, there's no such thing as a 10th life, but unfortunately for you, physicists love 10th value layers. So I'm going to define a TVL, and you can tell me if my definition is correct or not. Here, we said that the half value layer is the thickness that reduces the intensity of the beam to 1/2. How about this though? A TVL is that thickness of an absorber that reduces the activity or the intensity by a factor of 10. The real question is it by a factor of 10 or is it to 10%? In other words, let's take a look at the answer. Maybe I didn't ask that very clearly. The TVL is the thickness that reduces the intensity of the beam to 10%, not by 10%, but to 10%. If we're by 10%, it would do this: 1,000, 900, 8,100, 7,200, 6,300. That's not what a TVL does. It's to 10%. A TVL goes from 1,000 to 100 to 10 to 1 to 0.1, 0.01, and so on. So make sure that you understand that a TVL reduces it to 10%, not by, but to 10%. And once you know how many TVLs you've got, you no longer care what that absorber is made out of or how thick it is. Now look what happens here. As we go through TVLs, we're not going to 1/2, 1/4, 1/8. Look what we're going to: 1/10, 100th, 1,000th, 1/10,000th, 100,000th, 1,000,000th. That's putting in TVLs. And as we take them out, we're going to multiply it. Every time we take out a TVL, we're going to multiply it by a factor of 10, then 100, then 1,000, then 10,000, 100,000, and 1,000,000. So the attenuation of radiation is only dependent upon one thing: n. What's the number of HVLs or TVLs? That should say TVLs. I'm catching errors here. So as you take the TVLs out, you're going to multiply by 10 for the first one, 100 for the second one, and so on. Now you're going to see the graph again, and this is still wrong. This should be an I, but the graph itself is perfect. Here we're at our I0. As we add in TVLs, the reading is going from the total value to 1/10, 100th, 1,000th, 10,000. And as we take layers out, we're going to multiply times 10, times 100, times 1,000, times 10,000, and so on. Now, this is a two-step problem. Number one, which stops more technetium energy, a TVL of lead or a TVL of aluminum? Who's got that? That should be easy.
They're the same?
Sure. A TVL is a TVL. We don't care what it's made out of. The answer is the same. But how about number two? Which stops more, a half value layer of lead, which is very dense, or a 10th value layer of aluminum, which is very lightweight?
TVL.
The TVL? Perfect. A TVL is going to cut it by a factor of 10. An HVL is only going to cut it by a factor of 2. This lead and this aluminum are just misleading. They don't even need to be there because it doesn't matter what they are. Once you've got an HVL, cuts it in half. Once you've got a TVL, cuts it by a factor of 10. A TVL of anything will absorb more radiation than a TVL than an HVL of anything else. So there are your answers. Now, how do we deal with the equations? So you've already seen this chart a couple of times. So as we go from 1 to 2 to 5 to 8 TVLs, how much penetrates? What can penetrate the first TVL? 1/10. If there are 2 of them, 1/10 squared, that's 100th. If there are 5 of them, 1/10 to the 5th, that's 10, 100,000. That's 10, 1 over 100,000, and so on. So look at how simple your formula is. 0.1 to the n. If you're dealing with TVLs, it's simply going to be 0.1. Now, here's where you have to be careful. I is I0 times. It's going to be 0.1 to the power of thickness over TVL, or it could be 0.5 to the power of thickness over HVL. But if this is 0.1, that has to be TVL. If this is 0.5, that has to be HVL. You cannot mix them up. You're guaranteed failure. And again, there's no TVL problem you cannot solve with that equation. Okay, let's take a look here. We have, let's say if we have 4 layers in place. Now, as you know, nothing is linear related to radiation. If it were linear, here's what it would do, 1,500 and 0. Nothing does that. But take a look. In HVL, we're going from 1,000 to 500, 250, 125, 62.5. TVL is going from 1,000 all the way down to 0.1. So how many times effective is a TVL as an HVL? How many times effective is a TVL as an HVL? This reduces it to 62.5. This reduces it all the way to 0.1. How many times is effective as a TVL? So it's going to be 62.5 divided 0.1. It's going to be 625 times as effective. If I started with 1,000, this went down to 62.5. This went down to 0.1. This is 160/25 of this. Okay. Now, here's what we're looking at. And this is just a little bit repetitious. But the important thing to note here is we have a monochromatic beam, and layer 1 is identical to layer 2, layer 3, layer 4, layer 5, layer 6, and so on. Okay? That's true all the way out, even if there are 10 half-value layers, only for a monochromatic beam. All right, here are 6 problems. They're working in your head problems. They shouldn't take you over 10 seconds. Here's a scenario. We have a monochromatic beam going through 4 identical half-value layers. And with those 4 layers in place, the reading is 100. If I take 2 layers out, I took out this layer and this one. So now I've only got 2 layers in here and not 4. What is the reading now?
400.
Perfect, 400. There you go. Because when you take 2 layers out, each one doubles. 2 times 2 times 100, 400. How about this one? Took out 3 layers. What is it now?
800.
Good, 800. And how about this one? We had 4. Now I put in 6. I added 2 layers. It had 100, but I put in 2 new half-value layers. Now what's the reading?
25.
Perfect, 25. You have mastered this. Let's make it a little bit harder. The same questions, but these are TVLs. Monochromatic beam, 4 identical TVLs, reading is 100. If we take out 2 TVLs, the reading goes from 100 to...
Would it be 2?
No, it goes from, that's T, not the number of 2, but TO. The reading drops from, it goes up from 100 to what value?
The 1.
No, you remember you took 2 layers out. You didn't put them in, you took them out.
Would it go up to 1 million?
Nope, but multiply it again. Start with 100.
Oh, times 10 is 1,000.
Okay, so the first one's going to
Is
multiply
it 10,000?
10,000, right? The first one multiplies this by
10 years ago.
10,000, multiply it by 10 again, that gives you 10,000. How about if we take out another one? We had 100, we took out 3 10th value layers. Now what is it?
100,000.
Good, 100,000. And how about this? We had 4, reading is 100 with 4 layers. We added 2 extra ones. Now what's the reading?
Is that one 1?
That one is 1. Perfect, right? Because it went from 100 to 10 to 1. Okay, I think you have the concept down perfectly. I don't think the concept's all that hard. Dividing by 2 and dividing by 10 and multiplying by 2 and multiplying by 10 are really not too difficult. Now, this is a problem from an old exam. You have a monochromatic beam going through 2 different absorbers. This one is 2 centimeters thick. We don't know what it's made out of, but we don't really care. It's 2 centimeters thick, and the HVL for technetium is 0.5. How many layers is that? How many half value layers is that?
4.
4, right? 2 centimeters divided by 0.5. This is 4 layers. How about this one? This one's 3 centimeters thick, and the HVL is 0.75.
Still
4.
4?
That's also going to be 4, right? So now, how many layers do we have altogether? 8, right?
8.
Now that we know n is equal to 8, here's how easy the math is. We have 8 layers. 1/2 to the 8th is 1 over 256. If you count on your fingers, or if you do it on the calculator, it's going to be 0.00391, or 0.391% of the beam that can penetrate. So you have to, on a problem like this, you just have to determine how many total HVLs or TVLs that you've got, add them up, and then 1/2 to the 8th gives you your answer. Now, everything we've talked about so far has to do with a monochromatic beam. We're going to talk now about a polychromatic beam. Nothing that we have talked about applies, nothing, because the layers become thicker and thicker as we go through them. By definition, excuse me, by definition, this first layer cuts out half of the beam. But remember, a polychromatic beam has low energy and medium energy and high energy and very high energy. So while the first layer cuts out half of the total energy, what is it getting rid of mostly? Low energy or high? So it's getting rid of mostly low energy. And what does that do? That causes what's called beam hardening. That means that the beam on average becomes stronger and more penetrating. So layer 2 is thicker than layer 1 because we're getting rid of more of the low and some of the medium and a little of the high. And layer 4 is going to be thicker than layer 3. But now, let me show you what has really happened. After 4 half value layers, it becomes monochromatic because typically 4 half value layers gets rid of all the low energy and all the medium and all the high and leaves only the very highest layer. And therefore, after 4 layers, this layer and this one are equal because it behaves monochromatically after 4 layers. Now, fortunately, we don't have any mathematics to do here, but you should understand that the first few layers are going to increase from 1 to 2 to 3 to 4, they increase. Now, it took me a long time to put this together, to spend 30 seconds on it, but it'll give you a sense of what's happening here. We start with 4 high, 4 medium, and 4 low energies. The first layer cuts out half of the total, but look what it did. It only got rid of 1/16 of the high energy, 1/4 of the medium, but half of the low. The second layer is going to be thicker. That got rid of 1/4 of this, 1/2 of this, and 1/2 of this. And the third layer got rid of all the low, almost all of the medium, and a more significant amount of the high. And after the fourth layer, look what happened. We now have 0 low, 0 medium, and all we have is the highest. So now it behaves monochromatically. And these 2 bars go to 1 bar, which goes to 1/2 of a bar, which would go to 1/4 of a bar, because after 4 layers are in place, it behaves monochromatically. Okay. Now, true or false? By definition, 1/2 value layer reduces the beam intensity to 50%, and the TVL reduces the intensity to 10%. That is all true. We know a 1/2 value layer cuts it in half. The TVL cuts it to 1/10. But true or false? 1 TVL is exactly 5 times as thick as 1 HVL. We know it cuts out 5 times as much radiation, 50 to 10, that's a ratio of 5 to 1. But is a TVL 5 times as thick as an HVL? True or false? So I'm going to give you a hint. That is a linear extrapolation. And therefore, it cannot possibly be true. In fact, here's what we would have to do. Mu, the linear absorption coefficient, recall that was 0.693 over HVL. 0.693 happens to be the natural value, natural log of 2. So we could say mu is a natural log of 2 over HVL, or the natural log of 10 over TVL. And now look at this. If we take the ratio of 10th value layer to 1/2 value layer, the ratio is the log of 10 divided by the log of 2, not 10 divided by 2, but the log of 10 divided by the log of 2. And so a TVL happens to be 3.3 times as thick as an HVL. On your calculator, if you want to try this, punch in the number 10 and the LN key, divided by the number 2, and then the LN key, and you'll come up with 3.32. Some calculators, like graphing ones, you're going to have to hit the LN key first, and then put in the 10. Okay, so keep in mind, a TVL is 5 times as effective, but not 5 times as thick. Now, for a monochromatic beam on logarithmic paper, we're going to get a straight line. It doesn't matter if they're TVLs or HVLs. This is a logarithmic function. We're going to get a straight line. And here you can see that the distance from here to here to here to here to here, they're all equal. Layer 1 equals layer 2 equals layer 3 equals layer 4. But look at the polychromatic beam. Even on log paper, it's not a straight line at all. It's a curve. And so it's very difficult to do mathematics, but it's easy to read off the curve. But you can see here that the first 1/2 value layer is this long. The second 1/2 value is this long. The third is much longer. And the fourth is so far out that that's where this line comes very close to this one. And that's why after 4 1/2 value layers or TVLs are in place, the beam becomes monochromatic because we got rid of all the low and the medium energies. Okay, let's work a couple of problems here. We're going to run over a few minutes. I hope that that's okay. But we did a lot of math today. If the HVL is 0.2 of a millimeter and the barrier is 0.3 of a centimeter. Now, it's very common on board exams for the question to mix up the units. And so you have to know that a centimeter is 10 millimeters. So you have to get these in the same units. It could be 0.3 centimeter and 0.02 of a millimeter, or this could be 0.2 millimeter and this could be 3 centimeters. The question asks, how many HVLs? What fraction can penetrate? So 0.3 divided by 0.02 or 3 divided by 0.2 is 15. We simply say 1/2 to the power of 15 equals, and the value is not 0. Someone asks you, if you put 15 1/2 value layers in place, does it drop the reading to 0? The answer is no. For all practical purposes, yes, but in reality, no. It drops it at 0.00003. That's 1,000th of 1%. Okay. Here, we have a reading of 100. The HVL is 4.5 millimeters. The thickness is 1 centimeter. That's 10 millimeters. So we have 10 divided by 4.5. We have about 2.2 HVLs. That means that it's going to drop it to a little bit more than 25%. So it's going to go from 100 to 50 to 25 plus a little bit more. And let's see what that comes out to be. So we have 100 times 1/2 to the power of, in parentheses, thickness divided by HVL. Here are your keystrokes, 21.4. Our linear guess was a little bit more than 20. Pretty good guess. I'm going to skip problem 3 and problem 5 because they require these very extensive logarithmic manipulations. How about this one? If the TVL is 0.3 of a centimeter and the thickness is 1.2 centimeter, okay? How many TVLs is that? Who's got it? How many TVLs? 1.2 divided by 0.3. That is going, good. That's going to be 4 TVLs. What fraction can penetrate it? 1/10 to the 4th. It's that simple. We have 4 TVLs, 0.1 to the 4 on your calculator, 0.1, y to the x key 4 equals, and you got a bunch of right answers here. It could be 1/10,000 if you count on your fingers. It could be 0.0001. It could be 1 times 10 to the -4. All of those are correct and equivalent answers. Skipping problem number 3. This is identical to the problem we worked with half-life before. Mu, the linear absorption coefficient, is 0.0693 centimeter to the -1. Remember I told you before, if I saw that number, I would think, oh, 0.693, something's going to cancel. The original reading is 100 and the barrier is 10. So let's take a look. We're going to solve first for HVL. We don't know what that is. The linear absorption coefficient is going to be the half value layer is going to be 0.693 over the linear absorption coefficient. That's 0.693 divided by 0.0693, 10 centimeters. This said we had 10 centimeters in place. 10 centimeters happens to be the half value layer. We have 1/2 value layer in place. 1/2 of 100 is 50. And I think after this, 2 more problems and we're done. Again, this is a pattern recognition problem. You do not need a calculator. And I'm going to wait for a correct answer here. You have a source, the intensity is 4 MR per hour. You place the 4 centimeter barrier in place, and the reading dropped from 4 MR per hour to 0.4 MR per hour. What's the 10th value layer? Who's got it?
4 centimeters.
4
centimeters.
Excellent. How many half value layers is that? By definition, if it went from 4 to 0.4, that's by definition 1/10 value layer. So 4 centimeters has to be the 10th value layer. 0.4 of a centimeter. Again, you could work it out logarithmically, but that is just pattern recognition. If it went from 4 to 0.4, it's a TVL. If it went from 4 to 2, it's an HVL. Okay, and one more very simple problem. The first half value layer of a polychromatic beam is 3 millimeters. What can we say about the second half value layer? Thicker, thinner, equal to?
Thicker.
Got to be thicker, 100%. What do we say? The layers, the first 4 layers, each is thicker than the one before it. And here's a very lengthy discussion of that. But the bottom line is we have beam hardening and it's going to be thicker. Okay, we're going to stop here. We're going to start next time with inverse square law. It's a very important concept. It appears on boards all the time. We're going to spend probably the first 10 minutes of our next lecture, next Thursday morning at 9 o'clock Central Time on inverse square law. And then we will continue with the rest of whatever is next. I can't remember what it is. It might be radioactive decay. I'm not sure, but that will be next. So I'm going to see if anyone has any questions before we terminate the session today. Anyone? Any questions about anything we covered from either of the lectures? Anyone? Okay, if not, as I will do on every lecture, I thank you for your attention. I thank you for participating and guessing and answers. It's a lot more fun for the speaker if people participate. So I'm glad that you're all doing so. Hope you have a great week, and I will see you 166 hours from now right here online. So,
Thank you.
Thank you.
Thank you.
Thank you.
see you.
Thank you.